Hello, everyone. Our project is supposed to solve the idea of poor image quality. So our model is supposed to have the image restoration. Our problem statement would be having historical or old images of poor quality, and then we're going to enhance its quality using deep learning, or specifically our denoising convolutional neural network model. This is an example of a historical image which was restored.
Okay, so our primary paper was called the DNCNN. It mainly consisted of using a denoising convolutional neural network, which we will be discussing later on. There were many models, including the diffusion model and the variational autoencoders. However, this one generated the lowest loss or the lowest PNSR. This model used a filter type that's known as the Gaussian filter and had 5 data sets. All of them were grayscaled and were used for image denoising. They consisted of various types of images. For instance, the Urban 100 consisted of urban layouts. The Berkeley, which is the BSD, consisted of facial images. And the set 5, 13, and 12 were all noisy. In addition to the rest, were all noisy grayscale images that were randomly generated.
So we had three models that actually solved the same problem, one of which was the denoising convolutional neural network. And that actually uses the idea of pattern detector, and it detects noise as a pattern. The variational autoencoder actually condenses the input into something small, and then it resolves this and gets passed to the decoder in order to have it for a bigger size as the output. The diffusion model is a kind of a generative model which generates noise in high resolution images in order to train the model, and then it gets resolve the noise in order to have the high resolution output.
Okay, moving on to our DNCN architecture. Basically, the input is a 2D image, which is in grayscale. And the architecture basically follows a homogeneous architecture where a convolutional layer is applied along with the batch normalization and ReLU to add non-linearity. And the convolution layer basically uses a kernel of 3 by 3 throughout the entire architecture, moving forward to produce a residual image or a differentiation or a differential image as the output. So we faced several characteristics that we wanted to propose several solutions on, including that the dataset only consisted of fixed square grayscale images. It was also augmented with only 90 degrees rotations and flips, which we want to enhance and maybe add more techniques. The learning rate was initially 1 milli, and by the end it was only 0.5. The layers were all homogeneous, as mentioned, fixed with a convolutional layer, a ReLU, and a batch normalization layer. Our solutions consist of adding more augmentation, or we want to tune the hyperparameters, including the learning rate. We also want to stack layers together, meaning we want to add a set of convolutional layers along with the nonlinearity and the batch, and then we add a pooling layer in the middle, and then we would want to implement several and we would also want to implement several heterogeneous data because our data was only fixed square grayscale images. So we would want to add more colored images with the RGB images and introduce more heterogeneity in general.
So the original model, in order to get deployed, we had to run the model on a NVIDIA GPU, something that would make the process speed up. Also, what we found out was the loss that we had, the PSNR, which is the peak signal to noise ratio, was 160. So in order to have it actually to fasten things up, we had the original number of epochs, which was 300, reduced to 20, and the number of iterations per each epoch was 2,000 in the original model, but we changed that to 20 to make it faster. What we actually had after we actually changed the model, we tested the model with different optimizers, including the stochastic gradient descent and the RMS propagation. We also changed their initial learning rates, but actually we found out that Adam and the initial learning rate that the baseline code had were actually the best. We tried substituting the convolutional layers, which were 2D to 3D, in order to adapt for 3D images, so colored images. And we grayscaled the div2k dataset, which was supposed to be colored, in order to test it on our model.
Okay, so these are the baseline results. It is noticed that by the end of the results, after the iteration of the 300 epochs all in all, this basically consisted of, it took around 26 hours on a standard CPU, and it was the loss of around 160 PSNR, and the initial results.
When we tried to have the stochastic gradient descent with a moment of 0.1 as an optimizer, we actually got the least, after the 20 epochs, the least noise level was 1,134. And when we tried the RMS propagation as an optimizer and the cross entropy as a loss function, we actually yielded not a number as a result, which means that it was very high.
Okay, so our findings consisted of, firstly, we had to use a GPU for the images because they took around 26 hours on standard CPU. So when it was run on the P5000, I'm sorry, GPU, it took around 2.5 hours. The data trainings were only, as mentioned before, 2D images, which were grayscale. The models were ReLU. The regularizer was also batch normalization. The convolution layer was 64 filters, all 3x3, and used same padding. The data shape was heterogeneous, and it should be handled in the data generation phase, which is in a separate file. So our next steps and timeline consist of, we will try to adapt or to adopt different sizes of images, and this would be by 27th of October. We also want to ensure that our model, you could say, fits colored images, and this would be by the 3rd of November. And we would also want to add more data augmentations, which is also on the 3rd of November. And these are our contributions, and we hope you have enjoyed the presentation, and thank you.
Thank you.